Fears of the Y2K bug are keeping many people grounded, and most say they'll settle for being close to home with family and friends.
The computer chip is ruling the evening, absolutely.
Todd and his family are preparing for the downside of Y2K should it come to pass.
Chicken noodle.
They've stocked their shelves with soups,
Chicken noodle.
more than you'd find in some convenience stores.
Chicken noodle.
Dire Y2K predictions aren't tough to find. Just get in front of a computer, the very device behind this whole millennium mess, and click around the always freewheeling web. A plunge into darkness, societal collapse, World War III, alarming New Year's scenarios for sure.
A little while ago, I was at a birthday party and someone brought up the topic of the Y2K bug. So, how about that Y2K bug? This also works great as an icebreaker for first dates. And if you're not familiar with what the Y2K bug actually was, around the end of the 20th century, engineers started sounding the alarm that there were going to be potentially catastrophic computer problems all over the world, right as the year 1999 ticked over to the year 2000. I really can't overstate how much of a cultural phenomenon this was at the time. There was constant media coverage. I was a kid when it was happening, but I remember it being on the evening news and my parents talking about it with their friends. And some of it was obviously hysterical, claiming that planes would fall out of the sky and banks would fail. But then the millennium came and went, and nothing much really happened. People spent the next 25 years arguing about whether it had all been blown out of proportion, or whether it was because so much effort had been put into fixing it that there weren't any major issues. Now, whenever the Y2K bug gets brought up, the explanation that someone always gives is something along the lines of, computer memory was prohibitively small and expensive in the 20th century, so for efficiency reasons, programmers only used 2 digits to represent the calendar year in dates. And what they're actually saying here is that instead of using the entire year, like 1999, and having to use 4 digits, programmers just used the last 2 digits, 99, to represent the year. So instead of ticking over from 1999 to 2000, we get this issue of 99 kind of wrapping back around to 00. And then when computers try to compare the 2 dates together, they would mistakenly think that dates from the year 2000 were actually 100 years in the past. And so at this point, I'm nodding along to these similar anecdotes I've heard a number of times before, and I just start to get this feeling, it's kind of like having a stone stuck inside your shoe, except it's inside my brain. And the thing that's really ringing the alarm bells in my head is this bit about programmers only using 2 digits. Because what actually is a digit? Well, the way that most people think about digits is in terms of the modern Western number system called decimal or base 10. And all that means is that there are 10 different symbols to choose from to represent numbers. So you can represent numbers up to 9 using a single unique symbol. But if you want to go one more than that, you've run out of symbols to use. So the way that we've all agreed to represent larger numbers is to use more than one symbol at a time. You would have learned in school as a kid that this column on the left is how many 10s you have, and this column on the right is how many 1s you have. And when you have more than one symbol at a time like this, each individual symbol is called a digit. It's super basic, I know, but I promise it will be important later. And so if we take this concept and apply it to the number 99, let's walk through what happens when we increase 99 by 1, like we're ringing in the new millennium. We add the 1 to the 9 and get 10, which is now too big to fit in the 1s column, so we do this thing called carrying the 1 into the 10s column. 9 plus 1 is 10 again, so now we need a new third column or third digit to represent the hundreds. But because programmers only use 2 digits to save space, the one that's in the 100 column gets lost, and we end up with just 00. So this is referred to in programming as an overflow, and I can confirm for you that it's a very real thing that still happens all the time. So it's totally believable to me that Y2K could have been caused by an overflow. But I keep thinking about the concept of the date overflowing when it goes from 99 to 100. And as a programmer myself, there's just something that's really bugging me about that explanation. The reason I bothered to go through how our base 10 number system actually works in the first place is because if you know a bit about how computers work, you'll know that they actually don't use base 10 to store numbers. They use something called base 2, or binary. And binary seems a bit intimidating to a lot of people, but it's actually extremely simple. It's almost the same as base 10. The only difference really is, you know how base 10 has 10 different symbols that you use to represent numbers? Base 2, yep, you guessed it, only uses 2 symbols to represent numbers, 0 and 1. And in exactly the same way that we run out of symbols when we want to go above 9 using our number system, in binary, obviously we run out of symbols when we need to go above 1. And in exactly the same way as base 10, when we need a bigger number, we just add another digit. Now the only difference really is that in base 10, the columns that we use represent multiples of 10. So you have the ones column, the tens column, the hundreds column, the thousands column, and so on. In base 2, the columns, predictably, are multiples of 2 instead. We have the ones column, the twos column, the fours column, the eights column, and so on. So if we take a base 2 number like 1110 and we want to know what it is in decimal, we just add up the columns, exactly the same as base 10. We've got 1 8, 1 4, 1 2, and 0 ones. 8 plus 4 plus 2 is 14. So these two sides are actually exactly the same number, just represented using 2 different bases. And if we turn our attention back to the number of the hour, 99, how would 99 be represented in binary? Well, it looks like this. We've got a 1, a 2, no 4s, no 8s, no 16s, 132, and 164. And if we add them all up, we get 99. So when we're adding 1 to 99 in base 10, we ran out of digits and had an overflow. But what about adding 1 to 99 in base 2? Well, addition actually works exactly the same way in base 2 as it does in base 10. We try to add 1 to the ones column here, but it won't fit, so we carry the 1 over into the twos column. The twos column is already full as well, so we have to carry again, but the fours column is empty, so the 1 just goes in there and we're done. But wait a second, wasn't the whole explanation of the Y2K bug that the year overflowed when it tipped over from 99 to 100? That doesn't make any sense because that particular overflow only happens in base 10, not in base 2, which is how computers store numbers. In fact, the only way to cause an overflow by adding 1 in any base is if all the digits in the number are already at their maximum value. In base 10, if all the digits are 9, then adding 1 will cause an overflow, whereas in base 2, all the digits have to be 1 to cause an overflow. And you can clearly see that 99 in base 2 isn't all 1s. So at this point, I'm just thinking like, what on earth could have caused an overflow going from the number 99 to the number 100? So I start galaxy braining, thinking like, maybe they did something like split the number into 2 groups of 4 binary digits, but that doesn't make any sense either, because obviously if you look at how 9 is represented in binary, it's not going to overflow at 10, plus what's the point when you can represent just binary? Hey man, are you okay? What? No, yes, no, I'm fine. I was just thinking about something. You know what? I'm gonna go get another drink. So at this point, I did what any normal, well-adjusted person would do. I pretended to go get a drink so I could leave the room and start Googling technical explanation for the Y2K bug on my phone. But surprisingly, I can't really find anything that actually explains the thing that I'm thinking about. The answers I find on Stack Overflow all kind of boil down to they used 2 digits to save space. The Wikipedia article has a section on the cause of the bug, but doesn't mention anything about the fact that binary numbers don't overflow at 99. So I gave up. Well, I actually did give up. But sometime later, I was going through this fantastic course by Pikuma where you build a game for the Nintendo Entertainment System from scratch. This console's from the 1980s, so the technology's very different. And in the introduction of the course, he mentions that the company Ricoh that made the chip that ran the NES managed to avoid a patent lawsuit on the design of the chip by removing something called binary coded decimal, or BCD mode for short. So I go look that up on Wikipedia and it all suddenly just clicks into place. Here we go. So as we just discussed, there's more than one way to represent the same number. We could almost say that base 10 is like a human-readable form, and base 2 is like a machine-readable form. And what that means is, when a human is typing a number like 99 into a computer, they expect to be able to type it in base 10, rather than typing it in with a bunch of ones and zeros. It then needs to be converted to binary for the computer to actually store it and work with it, and then later, it needs to be converted back to base 10 if someone wants to read the number on a screen. Well, as it turns out, this process of converting back and forth between binary and decimal is actually quite computationally expensive, especially for older machines that were produced from the 1950s through the 1970s. One of the approaches that engineers came up with to deal with this problem of conversion between binary and decimal and back again was this special binary coded decimal mode that I mentioned earlier. And the way that BCD mode works is that rather than storing a number like 99 as a single base 2 number, we store each digit of the base 10 representation of 99 as a separate binary number. You can see in the BCD representation here, it's the same 4-bit pattern, 1001 or 9, repeated twice, which is quite different to the normal binary representation of 99. And there's a good reason for storing things this way. As I mentioned previously, if you want to convert this binary 99 into decimal digits to display on the screen, you have to do a whole bunch of computation. Use a logarithm to figure out how many digits there are, progressively divide by powers of 10, with division being very expensive on old computers, discarding the remainder, figuring out the digits. Whereas if you're using BCD mode, you just go through 4 bits at a time for each digit and then you're done. You might actually be wondering what the downsides are of something like BCD mode, because it seems like such a great idea. Well, notice how even for the number 9, there are still some zeros in there. With 4 bits, you can represent up to the number 15. So by only allowing the digit to go up to 9, we're actually wasting 40% of all of the memory that we have. So this 8-bit number in binary can represent up to 255, whereas with 2 BCD digits, we can only represent up to 99. The second reason is that arithmetic, like adding, subtracting, and multiplying numbers stored in BCD representation, requires more complex hardware than just standard binary. But all these downsides were considered a completely worthwhile trade-off in the early days of computers when everything was comparatively very slow. And so, to tie things up with a nice little bow, I eventually end up on the Wikipedia page for the IBM 9020, a system for use in air traffic control, which was one of the biggest things that people were afraid of during Y2K. This line of mainframes supported a decimal mode like BCD mode, and if you scroll down to the very bottom of the article, you find this section entitled Longevity, where it tells you that machines were eventually replaced at great cost out of probably unfounded concern that they would stop working in the year 2000. And at this point, you can probably already predict the reason that that link is purple and not blue. Yep, back to the original article we started with. So now you know. For me personally, this was an absolutely perfect example of the bell curve meme. I knew just enough about how computers work to think that the explanation didn't make sense, but not enough to realize that actually it does make sense. It's just leaving out an important part of the explanation. Programmers really were using 2 digits to conserve space. The problem is that nobody tells you why they were even storing individual decimal digits in the first place. I guess because if they did, then they'd end up spending 20 minutes explaining the whole thing like I just did, and if you do that, then you don't get invited to parties anymore.
World War III.
Chicken noodle.